Hello. Advanced ecological methods. This is my absolute favorite lab, the Piranha lab, the Piranha problem. I'm going to try to do this lecture as quickly and directly as possible. If you have already tried to do this problem set, you are ready for this lecture. I am asking you, please try it on your own. Think about how you might do it. And what you're going to do is you're going to go down sometimes some pathways that don't work out right. This is the solutions. Part of the practice here is actually doing things that don't work and finding out why they don't work. I can't really help you do that. That's something you have to do. So, and if you're in class, we did that in class a bit. We went down some pathways that didn't work. But let's go back and take a look at our central problem here. The problem looks like this in the lab handout. I've got this piranha tree here. I got a palm tree here, and I've got these two lakes, right? And I've labeled this one Pond A, and this one Pond B. Now, what has happened is Awankamo has gone out and he has planted some trees. These are the trees around this one. And essentially, he has added food to this lake, and he has added no food to this lake. And so the fundamental question is, he then collects, right? He then collects some stuff. And what he does is he collects pond, and I'm going to have to make it look like this. He collects a sample of n equals 9 fish. And those fish look like x1, x2, x3, x4, blah, 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 and down to x9. He has an x mean for those. And those look like this. Actually, the fish he has look like not a very good normal distribution. And the other one is Pond A, is a not so normal distribution either, but it's a bunch of fish that he collected. All right, and this is also n equals 9, x sub I through x sub 9, and he has an x bar for those. And that x bar is right down here. X bar for B is there. Sorry, x bar for A is down here, and x bar B. Because I reversed them on the handout, you have Pond A on the right and Pond B on the left. B is going to be larger by 10%, right? So we know that if we subtract those means, x bar B minus x bar A will equal about 16 is the difference between them, all right? So this is which is about 10%. We're going to be looking for this difference of 16, all right? So the question is, did the trees that Awankamo put there on the pond actually cause the fish to grow larger in that pond compared to the other? We can't really answer that question exactly, but what we can do is set up a null and an alternative. There are two possibilities here. And one possibility here is that the difference in fish sizes, in fish weight, x bar, is due to the added fruit. The other alternative, or the null, what I'll call it, is that the difference in fish weight is due to sampling variance. So this is where statistics, inferential statistics, sort of meets the road here. The rubber meets the road, if you will. You take a real life problem. Did Pond B actually have bigger fish? And then there's two options here. Either there are bigger fish in Pond B, or there are not. And if there are not bigger fish, then we explain the fact, the sample is bigger, right? There's no question. Awankamo caught 9 fish, they weigh more. Why? Is it because the fish are really bigger in that pond, or is it because it's simply sampling variance, and if he were to keep catching fish, they would be the same size in both ponds? And that really becomes once you get that done, you've got part of that's like a big part of the puzzle here. What you really want to know then is what we've been doing through all throughout our statistical work here is we've been taking a parent distribution that looks something like this. And we're asking it's going to have some mean value, and it's going to have some variance. And you're going to take 2 samples of 9 from that. So this is what the null looks like, right? This is the null hypothesis. You're going to have n equals 9 samples here and n equals 9 samples here. You're going to plot them on a graph, and they're going to look like this. And this is going to be pond A and pond B, right? They have means that are different from each other, and they are not exactly the same. This always happens even if they are taken from the same parent distribution. How far these are apart, right here, we can calculate the probability of getting these 2 means from a parent distribution. That we can calculate. And the way we're going to do that is we're going to simulate the parent. We're going to take out a bunch. We're going to repeat Awankamo's experiment. Awankamo's data. We're going to repeat his data 10,000 times. So you're going to go back and take 2 samples out of the parent, and then you're going to look at their means, right? You're going to take the 2 samples, and then you're going to find x bar A minus x bar B equals x bar difference, essentially, right? And you're going to look at that difference, and you're going to do that x bar D, x bar D, x bar D 10,000 times. And this will give you an idea that if you repeated this experiment and you took the 2 samples from the same parent distribution 10,000 times, how many of those times would you have a difference as big as Awankamo's difference or bigger? Now, I've told you that magic number was 16 for Awankamo, right? Not 16 factorial, just 16 exclamation point, like I'm excited, all right? So 16. How many times did you get 16 or bigger? And that number of times out of 10,000, there's a number of events greater than 16 out of 10,000 is going to be your p-value. That is the proportion of times you had a difference greater than 16. And I'm actually going to do, for this class, I'm going to do absolute value of 16. I'm going to do that because when we look at these 10,000 samples, they'll actually be centered on 0, like this. These differences of x bar A minus x bar B. Because most of the time, the difference should be 0, because as often as not, A should be bigger than B, and then B should be bigger than A. So really, they should all average out to be 0, which is fine, but you have these 2 tails. Sometimes B is bigger than A. These are extreme, right? These are extreme positive, and these are extreme negative. And if you're doing x bar A minus x bar B, a negative number is big B, which means that, and these are big A's, right, down here. So if the, did I get that right? No, I didn't, did I? Okay, let's try that again. Let me try that again. Redo. When this number is really positive, that's for a big A. And when it's negative down here, it's for a big B. So we're talking about the average score will be, when it's really large, for B, like in the case where Awankamo is correct, those extreme cases, 2.5% of them up here, 2.5% up here, those extreme cases on this end are cases where B is really big, and there's also going to be some extreme cases on the other end. The concern here is that, whatever Awankamo is doing to manipulate these fish, it could be good, it could be bad. So what if he's actually making the fish smaller? Would you want to report that to the elder? And I think that you would. So anytime there's a difference that's bigger than 16, either because he's made them get smaller or because he's made them get bigger, that's what you're going to use. All right, so you add up everything that's beyond that point, and you get all the events that have occurred. That have occurred as a result of sampling variance alone. So if that percentage is greater than 5% of points, that's the 2 tails added together, right? Then if it's greater than 5%, then we should say that it's more likely than that it was due by sampling variance. If it's less than 5%, we say it was unlikely to be due to sampling variance. All right, so let's go back and take a look at that from a more practical perspective. You can do this repeating part. You know how to do this. You know how to take a sample of 9. That's 9 columns. You know how to take their average. That's their average. You know how to subtract those averages. You know how to drag all that down, 10,000 rows. That's not a problem. The problem here is how do you estimate this parent distribution? Now, what we do know, some things, you do have some information. And we talked about this in class the other day, and some people suggested that, oh, you could just do like a, you could just do a case where you could choose random numbers. And like, yeah, I guess you could do that, and you can make that random number range between like maybe 0 and 1 million, but that doesn't sound very likely. Do 1 million? I don't know. I mean, fish can't be nothing. Fish can't weigh nothing, and they can't weigh 1 million. So you narrow it down. Then we thought we might use the samples that we have. And we have some samples, and those samples, actually there's 9 and 9, right? 2 groups of 9 that are a sample of Amazon fish. And you could use their range, which would take it from like 36 to 120, 136, I think, was something like that range. And then, but we know that every fish is not equally probable to be drawn. This is not a uniform distribution. Some fish are more common than others, and we don't really know how common they are, but our best estimate comes from those samples that we have. So we go back to those samples, and we say, I need 2 parameters. I need the mean, and I need the variance of that parent, right? I need those 2 things. How am I going to get the mean? Well, I could use the mean of samples here, and that's a pretty good bet. That's because if the first sample, the 2 means we know from central limit theorem, we know that the mean of samples is an unbiased estimator of the mean of the parent. So if you have 2 samples and each has a mean, we know the mean of them is a good estimate of the parent distribution mean. So we can take, to get x bar, and I'm going to write this information in red, and I'm going to actually give myself a bigger pen. To use this x bar here, what we're going to use is x bar A plus x bar B divided by 2, which is x bar A plus B, okay? So that is the best estimate of the parent that they came from. Now how about that variance? Well, what I talked about in class was the idea that, say you took a sample of n equals 9, and you got a variance of that sample that equaled 5. And then you did another n equals 9, and the variance of that sample was 6. Now, if you had those 2 samples from the Amazon fish universe, and you had to guess from another sample of 9, what would be the standard deviation of that, or the variance of that? It doesn't matter which one you do. The variance of that one, oh geez, well, you could try adding the 2 previous ones together, but that doesn't seem likely. It turns out that the average of these 2 is your best guess, right? So really what you would do is take s squared 1 plus s squared 2 and divide by 2, and that would give you the average of the s squareds, right? And wouldn't that be a nice, because that, of course, 5.5 is the expected value. You've already got 2 samples. And so it turns out that you also did this in your n-1 practice simulation, where we simulated the parent distribution variance from samples, and we found out that this variance of a sample was an unbiased estimator of the parent distribution variance. So on average, it will yield the correct variance. And so what we have now is we know that we have 2 samples from that universe back here. We have this one and this one. So we can calculate the standard deviation of each one, or you could use the variance and square root later. We have the standard deviation of A, and we have standard deviation of B from the samples, right? As calculated from your sample, like the 9 different things, right? And we used n-1. So I'm going to write standard deviation. So if you take their average, which is the standard deviation of A plus the standard deviation of B divided by 2 is equal to the average standard deviation of A plus B, right? That's a great estimator of the parent distribution standard deviation. In fact, it's the best estimator that we have because we have 2 estimates of Amazon fish. So the mean of the standard deviations is a good way to go. And this equation, by the way, is stdev dot s, and which is from a sample. And we have the average. So now we have these 2 pieces of information, this one here and this one here. So we can create a normal distribution with a standard deviation equal to the average of the 2 samples and a mean equal to the average of the 2 sample means. And that is a great place to start for our parent distribution parameters. And then we can go through 10,000 times and draw out samples, and for each sample look at the difference, and then we're going to take them out and put them into a sort them, rank them from top to bottom, right, or smallest to largest, and then we'll use those to figure out the how many times each kind of event has occurred. All right. That's it for now. This is the key. This is the how-to. Is to go back to Awankama's original 2 samples, and this is what we do in statistics all the time. So this is great. This is a t-test. I love this. This is great. I hope you love it too.